Okay, so I'm sorry that last video cut off abruptly, but for some reason, if I go over 15 minutes, YouTube acts crazy and all that good stuff. But anyway, so we're back here, and I'm going to go back over the facts that are equivalent. So if F, and what I've decided to, this will be 3 videos, but for Friday's class, you'll only need to watch the first one and this video, and then I'll save the other one for class on Monday. So let F be a polynomial function, R be a real number. Then the following are equivalent. 1, x equals R is a 0 of the function. And remember, to find your zeros, you set your function equal to 0, right? So x equals R is a 0 of the function. And so if x equals R is a 0 of the function F, then x equals R is a solution of the polynomial equation f of x equals 0, because it's a 0, right? And then not only that, but you also have the fact that if x equals R is a 0 and it's a solution, then x minus R is a factor of your polynomial. And if all that's true, then R0, the point R0 is the x-intercept of the graph. So with one valuable information, knowing one of your zeros, you get all these other valuable information. And so you make sure you keep this in mind as we graph later on in the chapters. We'll be coming back to that. Okay. So now let's find all the real zeros and determine the number of turning points of the graph of the function. Now recall in the earlier video, the turning points is just n minus 1 turning points. The graph of F has at most n minus 1 turning points. And turning points again are called your relative maximum or minimum. And that's where the points where the graph changes from increasing and decreasing. Okay. All right. So we can do the turning points first, right? Because all we need to do is find the degree of our polynomial, which in this case is what? 4, right? So our degree is 4, and so it'll be n minus 1. So 3 at most, 3 turning points. And I think we're going to graph, I don't know if it's this function. Yeah, we're going to graph this function too in a minute. So you'll be able to see, actually, yeah, we're going to graph this function in a minute. So you'll be able to see what's meant by turning points. Okay. And to solve for this, so I'm going to have you actually pause the video and solve for the zeros and then come back and watch the video. Okay. So hopefully this is what you have. You factored out, you can factor out a positive 2x squared. I would suggest factoring out a negative just because it makes your factoring inside the parentheses a lot easier because it's the difference of squares. But if we solve for x, so we'll get here, x is going to equal 0 once you simplify that. Here, x is going to equal 1, and here, x is going to equal negative 1. So we have 3 zeros and at most 3 turning points. All right, so now we're going to talk about something called a repeated zero. So let's say we have a factor x minus a to the k power, where k is greater than 1. Then this yields a repeated zero at x equals a of multiplicity k. And the thing to know about this, when k is odd, the graph crosses the x-axis at x equals a. And when k is even, the graph touches the x-axis but does not cross the x-axis at x equals a. And that'll come back into play when we graph our function. Okay. So here's some additional comments. To graph polynomial functions, you need to use the fact that a polynomial function can change signs only at its zeros. Okay, and we'll talk about that in a minute. Between any 2 consecutive zeros, a polynomial must be entirely positive or entirely negative. And the real zeros of a function divides, and we've only been talking about real numbers. I think we do get into complex numbers, but for now we're only talking about real numbers, no imaginary. So the real zeros of a function divides the real number line into intervals which the function has no sign changes. And again, we're going to talk about that actually for the remainder of this video. Okay, but just keep this in mind. And so now let's look back. So we're going to sketch this. So this is we're going to go through this thoroughly, and this is going to be all that you need to make sure you understand by class on Friday, and then the remainder of this section will be left for class on Monday, okay, with some additional notes. All right, so let's sketch the graph of this function here. Okay. So, and the steps are here. I put the steps down. So first we're going to look at the leading coefficient test. Then we're going to look at the real zeros. Then we're going to talk about any facts about zeros and graphing that we know. Then we're going to look at the turning points, although that really doesn't come into play, but I want to show you graphically what it means to be a turning point. Then we'll look at the real zeros, real line chart, which is very important. You're going to need to know, understand this and know this for future sections in this chapter. And then we're going to sketch all our graph from there. Okay. So let's see. So the first thing, the leading coefficient test, right? So we look, n is 4 and a sub n is -2. So that means we have even and negative, right? So that means, if you remember even and negative, that means both the terms will go down, right? So this tells us as x goes to, if they both go in the same direction, you can say as x goes to plus or minus infinity, f of x falls. Okay, the functions fall, right? And so that means, no, I don't want to write that, but we'll look at that in a minute. Okay, so we have our we've done our leading coefficient test. The second thing, the real zeros. Okay, we found those already, right? So the real zeros were 0. I'm gonna put them in descending order. -1, 0, 1. Okay, so we're good there. Now, what does that tell us? Well, since we have 3 zeros, remember those equivalent statements? We have 3 points, right? Namely the x-intercepts. So that tells us the x-intercepts are what? -1, 0, 0, 0, and 1, 0. All right. So if you need to go back to that page on page 3 to look back over that for those equivalent facts, you can. Okay. And in terms of, I'll put over here because I want to save space. So in terms of turning points, it's going to have at most 3. Okay. And so 5, which is sort of the heart of this graph, sketching this graph, is our real number line. So we draw a real number line. What's going on? Okay. My stylus went in automatic mode. We draw a real number line and we place our zeros on that real number line. So -1, 0, and 1 in the correct order. All right. And then we're going to place our function. So -2x to the 4th plus 2x squared. And in fact, my suggestion is, remember we factored this, right? So my suggestion would be to use the factor form because it's sort of easier to deal with, and I'll show you in a minute. So you can use either form, but sort of write the function next to it. Now we have to test any point. So what on that last page and everything, what that was saying is that since the zeros divide, the zeros of a function divide of a polynomial function divides your interval. Okay. And you have to test a point. So we're going to have to test a point, and you don't have to write these arrows down because I'm about to erase them, but we have to test a point in each interval. So we can choose any point we want. Remember, there's infinite number of points on the real number line. So we can choose any number we want, plug it into this function. That's why I say I would use a simplify, but if you have a calculator, you can use that. Plug it into either one of those functions, and you can get the value because then you'll have an extra point on your graph. But the purpose is to determine if the output is positive or negative, because that tells you. So we'll do this in a minute, but let's say we pick a value and that output gives us a positive value. That means every number between -infinity to -1 is positive, right? That also tells you that all your values will be above the x-axis. Okay, so I'm saying this in words. Hopefully you're writing down what I'm saying, but that means it'll be above the x-axis, and we'll see in a minute. But I'm gonna erase this now, and we have to do the same. So we're going to have 4 test value points that we're going to need. All right. And so you can pick any point you want. I would keep it simple. And so for this, we're going to do, in this first interval, we're going to test -2 because that's the value within that interval, right? You don't test your zeros because they're zeros, right? Zeros neither positive nor negative. Here we can test negative 1/2. Here we can test positive 1/2, and here we can test 2. So I really do want you to pause the video and input these values in the functions to get the output, because when you come back, I'm just going to give you the answers. Okay. So you should have received for your values negative 224, the point negative 224, negative 24. So that means it's negative. So that's why I don't like that. That's why I have a negative here, because that means any value from from negative infinity to negative 1, all the outputs will be negative. That also tells you that your graph will be below the x-axis. Negative means, so it's going to be graph will be below the x-axis. Okay. And from when I plugged in negative 1/2 into this function, remember I plugged into that function, I get 3/8, which is about 0.4. I estimated because we are graphing this. And so that was positive. So that means from negative 1 to 0, the graph will be above the x-axis. It's also positive from 0 to 1. And for 1/2, I got the 0.38. So it's going to be above the x-axis from 0 to 1. And then from 1 to infinity, I got 2 negative 24. So it's going to be below the x-axis, which makes sense if you think about it, because remember the leading coefficient test in 1 told us as x goes to positive and negative infinity, our function will go down. So that makes sense that these two are negative because it's going to be below the x-axis. Okay, so the first thing we can do is plot our zeros. So negative 1. Hold on. Okay, so I actually drew the graph because my stylus was really acting up and I didn't want to prolong the video. So what happened was, so I graphed, so you can graph, plot the points. So I plotted the zeros. Those are the zeros, right? And then I sort of estimated, although you should plot the negative 1/2 and the positive 1/2, 0.4. You can plot that so your graph will look a little more accurate than mine's. And then I sort of guesstimated down here with the negative 24 for the 2 and negative 2. But notice something. This is what I want you to notice. So I want to make sure your zeros are clear. You need to make sure those are clear. The other points you don't need them. You can use them just to make a more accurate picture, but you really don't need them. What's key is number 5, to know. So once you plot your zeros, right, then that tells you, you plot your zeros, then you go to 5 and look to see what's going on. And so you know from negative infinity, this first section here is saying from negative infinity to negative 1, all the outputs are negative, which means I'm below the x-axis, right? And so from number 1, we already knew that our long-term behavior of our function was that as x goes to positive and negative infinity, it's going down. So that's how I got it, and it's below the x-axis. Then from negative 1 to 0, I'm above the x-axis. And again, remember to make smooth curves. And so that's how you have sort of this hump right here. And then from 0 to 1, I'm still above the x-axis. So if you remember, in terms of, we have a multiplicity at 0. So since k is the multiplicity, we don't cross the x-axis, but we touch it, okay, at 0, 0. And then we're also, from 0 to 1, we're also above the x-axis. So that's how we have these two humps here, because again, we want to make smooth curves. And then from 1 to infinity, we're below the axis, and that's how we go down there. So these points, actually, you didn't need them. You needed to know the output. You needed to test a point within each interval because you needed to know whether it's positive or negative. And you can use these additional points to graph, but you really just need sort of the information we talked about. And so in the last 30 seconds, so in terms of our turning points, remember, they're also known as relative max min. If you think about it, that's sort of where we had our humps at in terms of our function, right? So here's the turning point. So we are increasing here, right? Then we get to this point right here, and then we decrease. So that's the turning point. Then we get to this and we decrease, and then we increase again. So that's a turning point. And then we go from here. This might go over a little 15 minutes, but I don't know. Then we go from here to here, and that's another turning point. Please ask questions in class.